So we've learned quite a bit now about aldehydes and ketones. We've talked about their key features. We've learned how to name them. We've discussed their physical properties and their oxidation and reduction. And now we're ready to move even further into the topic of aldehydes and ketones. In this section of chapter 14, we're going to be discussing hemiacetals and acetals, these are quite important because like the other features with the Tollens test and the Benedict's test, these hemiacetals and acetals will be very important when we discuss carbohydrates later on. So aldehydes and ketones come back in quite a fierce way when we discuss the carbohydrates that we'll look at in an upcoming chapter. Okay, so first of all, let's talk about these acetals and hemiacetals. So let's start with the hemiacetals. These are carbon atoms that contain a hydroxyl group and an alkoxy group. Okay, so they're sort of alcohols and ethers. They're formed when an alcohol adds to an aldehyde or a ketone in the presence of an acid catalyst. That's why we're discussing them here in the aldehyde and ketone chapter. And they can react with another alcohol molecule to produce an acetal, a carbon with two alkoxy groups, if there's enough alcohol molecules present. So sometimes there's only a 1-to-1 mole ratio and they stop at the hemiacetal. Sometimes there's additional alcohol present and you can go on to the full acetal. And notice in the first step where we add the alcohol, we form that hemiacetal where we form an OH and an OR group. Then if we go on with another molecule of that alcohol denoted here as ROH, we can form two COR groups, and then we get water, HOH, as a coproduct. We talked about that carbonyl group being a partial positive at the carbon end and a partial negative at the oxygen end, and that gave it a higher boiling point than we otherwise might expect, and so on and so forth in terms of physical properties. In terms of chemical properties, it makes it reactive. The alcohol, the oxygen specifically of the alcohol, those lone pairs, are attracted to the partial positive carbon of the carbonyl, and so that alcohol oxygen lone pair can attack the carbonyl carbon in an aldehyde or a ketone and add to it to form a hemiacetal. So we see here ethanal, an aldehyde, plus 1 mole of methanol per mole of ethanal in the presence of an acid catalyst. And notice it's a reversible reaction. That's those double arrows. It forms our hemiacetal here, which has a COC bond and a COH bond. If we have another mole of the methanol around, then we can go on to form the full acetal and be left with water as our coproduct. So just like in the case of aldehydes, the ketones are also reactive because of that partial positive in the carbon of the carbonyl, but they're less reactive than aldehydes because that carbonyl carbon is more positive in the aldehydes. In a ketone, we have carbon groups on both sides donating some electron density. In the case of an aldehyde, we have just the carbon group on the one side, the hydrogen on the other side of the aldehyde doesn't really have much to donate, right? It's a small atom. It has a relatively small electron cloud. So you get much more partial positive carbon in an aldehyde than in a ketone for that carbonyl carbon. So that's why we see ketones being less reactive because that carbonyl carbon is more positive, more partially positive in aldehydes than in ketones. You can, of course, get them to react, and we see here propanone reacting with ethanol to form the hemiacetal when it's a 1-to-1 mole ratio in the presence of that acid catalyst. If we have a second alcohol molecule, we can reversibly add a second molecule of ethanol in this case and form the full acetal. Okay, notice both steps are reversible just as they were for the aldehydes. Now, as interesting as the hemiacetals and acetals were in the examples we've used so far, when we get with cyclic hemiacetals, this is where we tend to see those carbohydrates that I mentioned being either aldoses or ketoses, aldehyde containing or ketone containing carbohydrates, and they can undergo this hemiacetal formation as we see here. So in glucose, which is a cyclic compound, a hemiacetal between this carbonyl carbon and the OH group on carbon 5 forms a stable 6-atom ring. So this is our typical way that glucose is found, right? You've got the straight chain glucose that we show here at the far left. That's unusual because it's much more stable to have it form that cyclic hemiacetal by having that oxygen from the OH group on carbon 5 attack that carbonyl carbon and close the ring to give us the hemiacetal form, the ring form of glucose that's present in about 99% of the glucose molecules. It is reversible, so we do have the straight chain also represented, but again, the overwhelming majority of glucose molecules are as hemiacetals rather than as straight chains. Before we go on, let's pause for a learning check. Go ahead and identify each of the following as a hemiacetal or an acetal. So pause the video here if you haven't already made the determination. Start back up when you're ready to check and see if A and B were correctly assigned. Good luck. Okay, so hopefully you were able to determine that in A you have a hemiacetal because you have that carbon with a COC bond there, that ether linkage to the top, and then a COH bond down below. So we have both an alcohol and an ether linkage off that same carbon. That's characteristic of a hemiacetal. In B, now notice we have a COC linkage above and a COC linkage below on that same carbon. That's a full acetal, and hopefully you assigned it as such. If these were too tricky for you, you stumbled, you're not quite sure what's going on, please try some additional ones in the end of the chapter and then reach out to me if it's still not making sense. Now that hopefully you're comfortable identifying hemiacetals and acetals, why don't you go ahead and draw one? Let's draw the condensed structural formula, or better yet, the skeletal structure of the acetal formed by adding methanol to butanal. So stop the video here while you show that, and then start it back up when you're ready to check your work. All right, so there we have it. We wanted the full acetal, so we expect COC linkages above and below the chain of the molecule. So we had butanal, so we had a 4-carbon chain. It did terminate with a carbonyl and an H, and so that carbonyl has now become 2 COC linkages. Since methanol was the alcohol reacted, it's a COCH3 and a COCH3 above and below, and that's our acetal. If we had stopped at the hemiacetal, then one of those COCH3 groups would be just a COH group. Hopefully you were able to draw that pretty easily. If you did run into trouble, please reach out to me, let me know where it went wrong, and we'll try to get you on the right track. So we looked at cyclic hemiacetals earlier. Now let's look at cyclic acetals. And these form when an alcohol adds to a cyclic hemiacetal, right? Just like any acetal formation is another alcohol adding to a hemiacetal. These are very important in carbohydrate chemistry, as I mentioned before. So if you're not so comfortable with the cyclic things now, we do see them here in this chapter, but they'll come back in force when we get into carbohydrates. So you will have another chance at this stuff. It's a type of linkage that bonds glucose molecules to other glucose molecules to form disaccharides. Maltose would be our glucose-glucose disaccharide, or polysaccharides like glycogen or plant starch or whatever particular form you might have. Glycogen's animal starch, and then what we normally just call starch is the plant starch form. So there you see it. We have our cyclic hemiacetal that we saw on the previous slide. We add another mole, in this case it's methanol, and this in the presence of an acid catalyst gives a reversible cyclic acetal. Okay, now notice we shouldn't have a lot of methanol in our body, right? The hemiacetal formed just by the OH group on carbon 5 of that glucose molecule closing in and making a ring, but to have another alcohol present, again, it shouldn't be methanol, biologically speaking. Probably would be a very bad thing to have much of in your physiology. So instead, let's look at a something that does form readily in biological systems. This would be the disaccharide maltose. So we have two neighboring glucose molecules interacting. So maltose is therefore a disaccharide made up of two glucose units and linked by that acetal bond, which we show in red. Right, so the carbon, each of those carbons on the other side of that bridging oxygen, we could look at as potential candidates for the acetal, but notice it's only the left carbon that it links that bridging oxygen that has a COC linkage. The right-hand one, we don't see that. We see it later on, but it's not that same carbon involved in the bridging oxygen that's bonded to another oxygen. So just be careful. Make sure you can identify each of those where the acetal carbon is in particular here. So it's produced by hydrolysis of starch from grains, malt, is another term for that whole process, and malted barley and things like that you might have seen elsewhere has to do with the maltose content. As I said, one glucose retains the cyclic hemiacetal bond shown in green, whereas the other glucose, it was shown on the left here, that other carbon is now part of an acetal as opposed to a hemiacetal. So the red is the acetal, the red oxygens on either side of that carbon, and then the green oxygens on either side of the carbon on the right molecule, the right ring, I should say, would be a hemiacetal. So we've got both an acetal and a hemiacetal present in alpha maltose. Finally, just a little more about maltose. I think I mentioned it already. It's a disaccharide. It's produced from hydrolysis of starches and grains, such as barley, and I think I specifically mentioned malted barley because that's a very common source. So hopefully that gives you a little bit of biochemical interest and gets you ready for that upcoming chapter on carbohydrates. If you're still struggling with acetals and hemiacetals themselves, please do try some additional practice problems. In this case, for chapter 14, we're not going to focus too much on the ring cyclic acetals or hemiacetals because they're going to be coming back in the chapter on carbohydrates.